Hello everyone, my name is Feng from Tsinghua University. Today I will introduce our paper PMF, a privacy-preserving human mobility prediction framework via federated learning. Mobility prediction problem to predict the next location is knowing the historical mobility trajectory. Sometimes it also requires to predict the corresponding visiting time. Here we focus on predicting the next location, following the recent successful practice from community. We find that model with better performance will also require more concentration of the training data. 10 years ago, they built one model for one user. And now, they build a centralized deep learning model for all users by training with all the data. When performance of previous models become here and here, the centralized requirement of training data becomes a risky choice because individual mobility trajectories are sensitive and they have many private information of individuals. Thus, we need to build a privacy-preserving mobility prediction model. And it should achieve competitive performance of current state-of-the-art mobility prediction model, but also it protects the user privacy. This learning-based mobility prediction model. Here present its framework. It first accepts the discretized spatial temporal point as input and use embedding table to translate them into vectors. Then we concatenate them together and use sequential model like STM to capture the sequential transition in the trajectory. Finally, we use a linear layer to project the hidden vector into the final predicted location. Based on this basic prediction model, we apply several techniques to protect the user privacy and improve the prediction performance. Here are the first step. We apply a learning framework to preserve the private user data in the local device, as left figure shows. In the conventional workflow, each user uploads their data into the cloud center and then obtain a well-trained model from it to complete the prediction task. After using learning framework, no user data is uploaded. Most of the training procedure is executed in the local device. We only need to exchange the model weights with the cloud server during several training epochs. This is the first step for protecting user privacy by preserving the raw data in the local device. When no user data is uploaded to the cloud center, we indeed upload the model weights to the cloud center. The risk of uploading weights is smaller than uploading the raw data. It also introduces large risk for leaking the visiting location list of user in the scenario. Attackers can pretend to participate in the whole procedure as normal user and then observe the changes of the location embedding table of target user during the training. In this way, attacker can obtain the information of visiting locations of target user. To protect user from this kind of attack, we propose to use differential privacy to add noise in the normal data for each user. Then the training of the whole model is divided into two steps. First step, training embedding table is noisy data while freezing other components. And the second step is to train other components with the normal data while freezing the embedding table. In this way, the changes of the embedding table is not deterministic, and attackers cannot easily find the right location visited by the user. With learning is a differential operation. The performance of our model is reduced. To further improve the prediction performance and make it competitive to the state-of-the-art model, we introduce a personal adapter in the local device for personalized fine-tuning after the normal training procedure. It works as an additional vector before the final output projection or correlation query, and is trained as executed in the local device to capture the personal pattern. We use 3 mobility data to evaluate the performance of our model, including 2 check-in data and 1 dense trajectory data. Here are the basic information of this data. Here is the result. You can find that compared with a model which protecting user privacy, our model achieves better performance. Compared with the joint model without protecting privacy, our model can also achieve competitive performance, while our model can protect user privacy. We present the results of privacy. You can find that compared with directly protecting data with privacy, the performance of our model is more stable when increasing the privacy requirement. It means that our model achieves a better trade-off in the performance and privacy protection. As a conclusion, in this paper, we investigate the privacy-preserving mobility prediction problem and propose several effective strategies to protect the user privacy while preserving the prediction performance. In the future, we need more works on developing efficient and effective optimization methods for the whole system to further improve the performance while protecting the user privacy. That's all.